In this section of Chapter 6, we will discuss molecular shape. Molecular shape is important, as we will see, because it gives rise to differences in the molecules, the way the atoms are arranged, and it gives rise to different polarities in the bonds, polarities in the molecule, and that has implications on intermolecular forces and many other things. We'll get there, we'll discuss them. First of all, here's some of the common shapes that we are going to talk about in this class. We can have a linear shape where the central atom is attached to two other atoms and they're in a 180-degree angle. Right? So this angle here is 180 degrees. You can have a bent molecule where the central atom is still bonded to only two other atoms, but instead of 180 degrees, that angle is bent. We can have a trigonal planar molecule where the central atom is bonded to three other atoms, and those are equidistant from each other, so they're bonded in the same fashion to the central atom, and they are the same type of atom. And you can see that these bonds, or the bond angles here, are all the same. So if you think of it as all of these atoms are in the same plane, where the terminal atoms, so the white atoms, are a triangle, and the central atom is right in the middle of that triangle. That's trigonal planar because they're all in the same plane, and trigonal for triangle. We also have trigonal pyramidal, where we have the same setup, but they're not on the same plane anymore. You can think of this as a pyramid, with the top being the central atom and the other three atoms making the base of that pyramid. Then finally, tetrahedral, where we have the atoms, the terminal atoms, there's four of them, forming a pyramid, and the central atom is not at the top anymore, but is right in the middle, in the center of that pyramid, in the hollow, right? If this were a three-dimensional pyramid, that would be right inside the pyramid in the center. That's a tetrahedral shape. We will be playing around with models in class, in lecture, but these are what they look like on the paper, right? And I will also give you a link to a simulation website where you can build your own molecules and you can move them around so you can see what they look like in three-dimensional space. This will be especially helpful if you are taking an online course. To determine molecular shape, we follow what is called the VSEPR model. So the valence shell electron pair repulsion theory or model. Big mouthful, that's why we abbreviated to VSEPR. And it states that the group of electrons in the valence shell of the central atom, they repel one another. So they're going to occupy spaces as far away as possible from each other. Think back to when we discussed the parts of the atom and we talked about how the electrons have a negative charge. And we also said that negative charges repel. Well, if I have negative charges spread around that central atom, whether it's in bonds or lone pairs, they are all negatively charged. So you can imagine that they are going to repel each other and occupy the space around the central atom as far away as possible from the other electrons. So we define an electron group. We're going to talk about electron groups around the central atom to determine the molecular shape. So electron groups are defined as either a lone pair or a bond. So it doesn't matter if it's a lone pair or a bond, they count as an electron group. Now the bonds, we talked about that when we drew Lewis dot structures. These bonds can be single, double, or triple bonds. We're not counting electrons, we're counting electron groups. So for electron groups, single bonds, double bonds, triple bonds, lone pairs all count the same. All count as one electron group. Not how many electrons are in those bonds or in the lone pair, but how many electron groups. And lone pairs, single bonds, double bonds, triple bonds count as one electron group each. Then we figure out from the table that I'm going to give you how the electron groups on that central atom are counted to figure out what the electron geometry is, the electron group geometry, and then how we get the molecular shape or the molecular geometry from the electron group geometry. So there are two different things that we're going to talk about. So make sure that you don't confuse the two. So how do we go about it? Okay, we are only going to look at simpler molecular shapes. In simpler molecular shapes, we're only going to count 4 electron groups around the central atom. When we did Lewis dot structures, we saw that we can have more than 4 bonds or 4 groups around the central atom, the expanded octet, for example, but we're not going to look at those molecular shapes. We're going to look at 4 and under. So if I have 4 electron groups around that central atom, how do I count them? What are the different possibilities? Well, I have 3 different possibilities. I can have a single bond in each of those spaces. So I can have 4 single bonds around my central atom A. And here's some examples of what some of the molecules that have 4 single bonds around the central atom. So CH4 has a carbon in the center with 4 hydrogens. NH4 plus, instead of the carbon, I have the nitrogen with 4 hydrogens around. CH2Cl2, I have a carbon bonded to 2 hydrogens and 2 chlorines, single bonded. So I can have 4 single bonds around that central atom. So when we draw Lewis dot structures, we're going to see if we have 4 single bonds, then we have 4 electron groups around the central atoms. Each single bond counts for 1. I can have another possibility though. I can have 3 single bonds and 1 lone pair on that central atom. I still have 4 electron groups around the central atom because each single bond counts for 1 and the lone pair counts for 1. So I have 1, 2, 3, 4. And here are some examples of molecules that have these particular combinations that have 3 single bonds and a lone pair on that central atom. I can also have a last possibility where I can have 4 electron groups around the central atom, but I have 2 single bonds and 2 lone pairs on that central atom. And here's some examples. I would suggest that you work the Lewis dot structures of these and see if you get these combinations. That would be very useful to you when you are trying to determine molecular shapes. What if I only have 3 electron groups around the central atom? This is the next, so a step down. Well, here's the combinations that I could have. I could have 3 single bonds around the central atom. Here's some examples of that. Remember that boron is that exception to the octet rule, that it can accept just 6 electrons. And here's that example. If I put boron here and then the chlorines on the outside, it has 3 bonds, 2 electrons each, 6 electrons around it, so not 8, but it's still happy. And it has 3 electron groups because each single bond counts as 1 group. So 1 electron group, 2 and 3 electron groups. I can have another possibility. I can have a single bond, a double bond, and a lone pair on that main atom. And here's examples of that. I can also have two single bonds and one double bond. So all of these count as one electron group. 1, 2, 3. Don't confuse them with the number of atoms around that central atom. I mean, the number of electrons, I'm sorry. This central atom in this example here has 8 electrons, 2, 4, 6, 8. But how many electron groups? 1, 2, and 3, because single bonds and the double bond count as one electron group. Those are very important things to remember to kind of differentiate. I'm not counting the total number of electrons. I count the total number of electrons when I'm doing Lewis dot structures and I want to see if my central atom is happy with the octet, if it's following the octet rule. But when I go to figure out molecular shape, I count single bonds, double bonds, and triple bonds, lone pairs as one electron group. And lastly, I can have a single bond, a double bond, and a lone pair on that atom. What if I have two electron groups only around the central atom? Here are the different possibilities. I can have a central atom that has two double bonds on each side. So, or one on each side, two double bonds altogether. So one on each side, one here, and these are counted as one electron group here and another electron group here. Here's another possibility. I can have one single bond and a triple bond. So one single bond on one side, a triple bond on the other side. Or I can have two single bonds only. And here's examples of all of those. Now, it doesn't matter, especially here, what side you put the triple bond and the single bond on, as long as the atom that's supposed to be linked to the central atom by a triple bond is on the correct side, on the triple bond. But it doesn't matter if you put the triple bond over here or the triple bond over here. It doesn't matter either way. So how do we determine then the molecular shape based on the Vesper model? We said that the electron groups will arrange themselves as far away as possible from the other electron groups. And that is because you have repulsive interactions between the electron groups, because electrons are negatively charged and they repulse each other. Now, the number of electron groups determines the electron group geometry, but the electron group geometry may or may not be the same as the final molecular shape, because that depends on how many atoms we have bonded to the central atom. And we're going to look at that in more detail. But if you were to use, so this is a simple pictorial of using balloons to illustrate electron groups. So if I have two electron groups around that central atom, you can see that the way for them to be as far away apart as possible is to be 180 degrees away from each other. If I have three electron groups around the central atom, they are going to arrange themselves in a plane, trigonoplanar shape, right? Where the atoms that are bonded, the terminal atoms are at the edges of the triangle, and my central atom is right in the middle of that triangle. And here's the tetrahedral shape. This is what it looks like, where I have atoms bonded at the edges of these balloons, and the center where they're tied together is my central atom. So you can see that the terminal atoms form a pyramid, and then right inside the pyramid is my central atom. So let's talk about how we determine molecular shape. Methane, so CH4 molecule, is an example where the central atoms are is bonded to four terminal atoms by single bonds. Okay, and we said that these all count as one electron group. So there's 4 electron groups. And if we go to that table and there's 4 electron groups around the central atom, I have a tetrahedral electron group geometry because my 4 electron groups are arranged. So I have 4 electron groups arranged around the central atom, and that gives me an electron group geometry of tetrahedral. Now, this is an example where the molecular shape is also tetrahedral because I have 4 atoms that are bonded to that central atom. So if I have 4 electron groups and 4 atoms, the electron group geometry will match the molecular shape and it will be tetrahedral. This is the case where I have the same electron group geometry. So I have 4 electron groups and 4 atoms around the central atom. The molecular shape and the electron group geometry will coincide, will match, and it will be tetrahedral. What happens if I replace now one of the atoms with a lone pair? Here's ammonia. Ammonia is NH3, and if I were to do the Lewis dot structure for ammonia, I would get this Lewis dot structure over here. Note that I have only 3 atoms bonded to my central atom. And for CH4, I had another atom here, and I had another single bond. Well, here I have 3 single bonds and 1 lone pair. So in this case, what is my electron group geometry? I count electron groups around my central atom. I have 1, 2, 3, 4, because that counts as 1 as well, the lone pair. So I have 4 electron groups. That makes my electron group geometry tetrahedral because I have 4 electron groups around my central atom. So the geometry of the electron groups is the tetrahedral. But because I've replaced that atom, 4th atom, with a lone pair, and I only have 3 atoms now bonded to the central atom, the shape of the molecule changes. It is now trigonal pyramidal. This comes because that lone pair occupies more space than if I had a single bond between the nitrogen and an extra atom over here. Since it occupies more space, it repulses these bonds more and it pushes them away. And so it forms this trigonal pyramidal shape for the molecule. The electron group geometry is still tetrahedral because I still have 4 electron groups. But the molecular shape is trigonal pyramidal, not tetrahedral anymore, because I replaced one of those atoms with a lone pair, and I only have 3 atoms instead of 4 around the central atom. What happens if I replace one more of those single bonds with another lone pair? Here's water. It contains, if I were to draw the Lewis dot structure of water, I would get this. And let's count the electron dense areas or electron groups around the central atom, which is oxygen. I have 1, 2, 3, and 4. Since I have 4 electron groups, the electron group geometry is still tetrahedral. But now, because I only have 2 atoms bonded to that central atom, and I have 2 lone pairs, the shape of the molecule becomes bent. So here's the progression. When I have 4 electron groups and 4 atoms bonded to the central atom, I have tetrahedral geometry for both. If I have 4 electron groups and 3 atoms bonded to the central atom. I have tetrahedral geometry for electron groups, but I only have trigonal pyramidal geometry for the molecule. When I go down and I have 4 electron groups around the central atom, but I only have 2 atoms now bonded to the central atom, I still have tetrahedral geometry for the electron groups, but the shape of the molecule becomes bent. Okay? Here is a table that will help you. I suggest that you print this out and have it sort of for your, when you do problems like these. If I have 4 electron groups, so here's the number of electron groups is 4. My electron group geometry is tetrahedral. Note that it does not change at all. If I have 0 lone pairs, so no lone pairs, all of them are single bonds, then I have a molecular shape of tetrahedral. You don't need to remember the bond angle. And here's an example of that. If I have 1 lone pair, note that I still have 4 electron groups, but now I have 1 lone pair and only 3 atoms. Then my shape becomes trigonal pyramidal, as in the case of ammonia. If I have 4 electron groups, I still have tetrahedral geometry, but if I have 2 lone pairs now, I have a bent molecule, as in the case of water. Here's the case when I have trigonal planar molecule. Okay, so I have 3 electron groups around the central atom. Remember, these can be 2 single bonds and a double bond. It can be 2 single bonds and a lone pair, or it can be 3 single bonds. Okay, so if I have 3 electron groups around that central atom, I have trigonal planar electron geometry. With no lone pairs, I also have trigonal planar molecular geometry. That is the case for SO3. If I have 3 electron groups, I have electron group geometry of trigonal planar, but if I replace one of those bonds with a lone pair, now I have a bent molecule. That's the case of SO2. And then lastly, if I have 2 electron groups around that central atom, I have electron group geometry of linear, and the molecule will also be linear. Now, remember we talked about the different cases where I can have a linear molecule. I can have 2 single bonds, I can have a single bond and a double bond, or I can have a single or 2 double bonds, or I can have a single bond and a triple bond. So all of those still have a linear shape, those molecules, and a linear electron group geometry, because I cannot really have replace an atom here with a lone pair. That it does not give me, it gives me a diatomic molecule. Here's the examples of the linear shape, right? We talked about that. We can have 2 double bonds. That's still a linear shape because I have 1 electron group, 2 electron groups. So 2 electron groups, even though they're double bonds, they count as 1 each. So here's the example of CO2. I can have a single bond and a triple bond. That gives me still 2 electron groups around the carbon. 1, 2. So a single, it doesn't matter if it's a single bond or a triple bond, they both count as 1 each, as the case of HCN. Or I can have 2 single bonds, as in the case of beryllium fluoride. And here it is. 1 single bond with 1 fluorine and 1 single bond with the other. And beryllium is happy even with just 4 electrons around it. It's one of those exceptions to the octet rule. How do we determine the shape of the molecule? So here is the way to do it. Here are the steps. Practice will help you to figure out the shape of the molecule, or if you have a polyatomic ion. But once you follow, so if you follow these steps carefully, you should have no trouble. But just make sure that you practice quite a few of these, because they can be a little bit confusing at first. It's something new you're not familiar with, so you just need a little practice. The first step, that's the most important really, is that you draw a correct Lewis-Dot structure. Without a correct Lewis-Dot structure, you will not be able to determine the electron groups around the central atom. So practice those quite a bit. I would go back, if I were you, and practice all of those molecular shapes that were in the table a few slides back, and you should see, if you've done it correctly, you should get those corresponding for single bonds or single bonds and lone pairs, etc., that were given to you in that table. So I would go back and practice those. Then you count the electron groups only on the central atom, not on the terminal ones, only on the central atom. And remember that these are electron groups. When we do Lewis-Dot structures, we count actual electrons to make sure they're following the octet rule, unless we have an exception, but those will be few and far between. So count up here with Lewis-Dot structures, count actual electrons. When you go to determining shapes, you count electron groups, not electrons. And remember, single bonds, double bonds, triple bonds, lone pairs, they all count as one electron group. And then use that table that was given to you. That's the kind of a simplified, condensed VSEPR theory, so that you can determine first the electron group geometry. Once you determine the electron group geometry, then figure out if you have any lone pairs, and that will dictate what the molecular shape is going to be. So if you have no lone pairs, the molecular shape and electron group geometry is the same. But if you start having lone pairs, then just move down that table to figure out. So if you have one lone pair, that will change it to a different molecular shape. Or if you have two lone pairs, it will be even different molecular shape. So these are the steps that you need to follow. And I would just practice quite a bit to figure out, using these steps to figure out molecular shape. Here is a sample problem for you to try. Determine the electron group geometry and the molecular shape for these two molecules. Follow the steps in the previous slide and give this a try. Don't be discouraged if you don't get it the first time. Just the problems are set up so that you can retry them as many times as possible.